Rear wings on cars aren't actually that efficient. In terms of all the regions of a car that are used to produce downforce, the rear wing only contributes to around 20% of the total, but it can easily increase the car's drag by about 10%. On the other hand, the underbody of a car is usually the main region producing downforce and often producing over half the downforce of the total of the car. And that only comes with usually around about a 10% increase in the drag. So overall, the underbody is far more efficient at producing downforce than pretty much anywhere else on the car. However, there's only so much you can do there and only so much you can get out of it. As such, rear wings are still added on almost all sports cars to improve the downforce and particularly over the rear wheels. One added benefit of that is if you have a rear-wheel drive or a four-wheel drive car, then more downforce over the rear wheels helps you get more power down to the road. But that doesn't make the rear wings any more efficient. So how can you make them more efficient and even more effective? That is what we're looking at today. And in this podcast, we're going through to look at a few different flow control devices that hopefully will improve the downforce and efficiency of the rear wing. They include something called a booster plate, then a gurney flap, and then what the authors of this paper call a separated wing, which is effectively just a slotted wing. And then on top of that, what happens when you tilt the wing up at one side. That's mainly to do with cornering. So in figure 17 here, we see this lopsided case, and this is actually pretty cool because a lot of CFD is really only to do with straight line focus. This has a cornering focus as well, with this rear wing tilted so dramatically. So to see how all these modifications affect a sports car's performance, we're looking at this paper called Influence of the Car Movable Aerodynamic Elements on Fast Road Car Cornering. So like always, it is open access and you can find a link below. So let's get into it. So over the past few months, we've covered quite a few papers from this research group actually. They're based in Poland from what I can tell, and they've always used the Polish supercar, the Aerodynamics Husaria, which we can see in figure 2, and I haven't learned how to pronounce properly either. So I think this supercar manufacturer was working with this university to develop some of the aerodynamics of this car. Now, to look at these various aerodynamic devices on the rear of the rear wing here, these authors decided to test them on a car while fast cornering and also during straight line speed. And that makes a lot of sense because these devices are there to increase downforce, which is exactly what you need to do during cornering, not necessarily during straight line speed. It's just kind of that it's very rare to see this kind of research, so it's quite important. In figure 3, we see the CFD domain they used. And you can see it has a bit of a curve to it, and it's quite big. It's about the size of a typical wind tunnel, but just has a curve, and it's like a 90 meter radius of curvature curve. And to simulate the curved nature of this flow, the researchers used a pretty novel technique of applying an MRF to the domain. So what does that mean? So this MRF thing, to begin with, MRFs are short for moving reference frames or multiple reference frames. Both are used interchangeably, and really, if you just say either one, it means pretty much the same thing. So what this actually means is that it has nothing to do with actually moving the flow. And in nerd talk, what it does is it adds an additional component to the momentum equations to simulate the rotation effect. In regular words, it is just saying that in each cell, okay, there is rotation here of this much. So depending on how far from the axis of rotation the cell is, then there is a certain rotational velocity associated with it, and you just apply that. So this approach can be a very good one, but one major assumption of it is that every cell in the MRF is rotating, which isn't always the case. At the end of the day, in some situations, the rotation that the air feels comes from the motion of the object, and the object won't impact every bit of air equally. So it can break down this idea. Here in this case though, it's actually pretty good because it is a global rotation based on a difference in paths the car will take and the air will take in total. So this is actually a pretty cool idea to simulate cornering. And after reading quite a few papers from this research group, they have pretty novel and out-of-the-box CFD approaches to difficult problems. And from what I can tell, the only author that has featured on each of these papers that I've read is this guy here, Babyface Christoph. So I think he is probably a good CFDer. Anyway, again, they have a good CFD setting of a thermal density of 5%, which is much more indicative of the real-life situation, which we've covered in other podcasts as well. And once again, like the paper we covered in podcast 200, they use an overset mesh approach to be able to move the various aero components around without having to remesh the entire domain. That again is a great idea, it saves a lot of time. Now in figure 5, we see their mesh, and I think that they actually simulated the entire car for this CFD, which is actually good. But I can't find anything about whether they used RANs or something else. I'm not sure if they used RANs, URANs, DES, whatever. They don't seem to talk about any time stepping or even turbulence models used. So I'm going to assume, based on the other papers, is that they use the same settings there, which is RANds with a K omega SST terminus model. It might not be, but I think it is because they have used that continuously. So it's cool to see the entire car now, because they only did half the car at other times. Now in figure 6, we see the Y plus values over the car, and it seems pretty much everywhere is below 70. Now, because I don't know what the terminus model is, I assume it is K omega SST, and if so, then this Y plus is fine, but I don't know. Interestingly, the rear wing has a much lower Y plus value than much of the car. It's well below 10, whereas a lot of the rest of the car is like 50 or so. So that suggests to me that the boundary layer mesh over the wing is finer than on the rest of the car, because sure, the roof, for example, will see a slightly faster moving flow than the refrigeration flow due to acceleration, but the wing should still be seeing at least quite fast flow. So it definitely isn't like only 1/5 of the speed. So as such, it looks like this mesh is finer on the wing than anywhere else based on the Y plus values. Now in figure 7, we see a really good grid independent study. It looks at 3 different configurations. The one on the left is just the regular car. So let me zoom in a little bit actually here. So this one is the regular car. Then the top right is for with the splitter plate. You can see this red little bit here down here. Then the bottom right is with the rear wing and no splitter plate. So the blue diamonds are for the drag coefficient, while the pink squares are for the lift coefficients, and the green triangles are for the front lift coefficients. And then the red circles are for the rear lift coefficients. So overall, there isn't too much of a difference across these different meshes, going from about 3 million cells up to 13 million cells, depending on the configuration. So most meshes seem pretty good. They don't actually say anything about this figure and which meshes they went with. So I have to assume again that it's the middle mesh, but it might not be. In other papers, they've done pretty good grid independent studies, so I think they probably use the same methodology here, in which case it would be the middle mesh. But again, that's an assumption. However, I'm not sure if that's a big deal anyway, because for the top 2 cars, it doesn't really matter too much because the finer meshes didn't change the results more than the general accuracy of the CFD anyway. For the bottom car, I guess that they should really go with the middle one, so this one here. That's because the meshes, as it goes higher, the results start to converge, but lower than that, there are a little bit of differences. So for example, this one here, which is 7 million cells, it's off by a few percent. So I'm not completely sure what they went with, but at least we have a nice looking figure here. Now, they also tell us that they compared their CFD results to their wind tunnel tests. And this is the wind tunnel test. So you can see they had their car in the Myra wind tunnel and then the CFD here. And they said that their CFD had a drag coefficient within 3.8% of the experimental results, and their lift coefficient was within 6.5% of the experimental results. So that's pretty good and quite a bit better than I was expecting. However, if they did go with the 10 million cell meshes from this grid independent study, then I guess that wouldn't be too surprising. I'm not so sure. So overall, from all of this, I think the changes, if we see greater than 10%, are trustworthy here. Given that there is a lot of information missing from the CFD method, it's hard to tell if it is more accurate than that. So I guess we should just assume about 10% from what we've seen. And just quickly, if you want to learn how to do CFD for your projects, including how to use OpenFOAM, which is a completely free and powerful CFD software but hard to learn, then take our courses in the link below. Let's move on to the results now. So first up is what they called a booster plate, which you can see in figure 10. Figure 9, you can kind of see it, but it's retracted. Figure 10 is where the good stuff is. So there is the main wing here, the big thing, and then there is this little plate behind it. And this is a really interesting design because it takes advantage of the flow that goes underneath the wing and uses it. At least ideally, it would use it to produce downforce. In that way, it's kind of like an air brake because no flow can go underneath it, really. What is the benefit of that compared to just extending the wing down to the trunk so that no flow can go through it? Well, it really seems like this setup with this booster plate is about halfway between the air brake and a rear wing. Because if you have just the rear wing extending down to the trunk and acting like a huge air brake, you get a lot of downforce, but you also get a lot of drag. So by having this little booster plate back here, you get some of that downforce because it's effectively an air brake too, but you don't get as much of the drag penalty, so depending on what you need. What's more, it also forces air over the suction side of the airfoil, which means that the suction side should see lower pressure, I think, at least around the leading edges at least. And at the very least, having this booster plate will make the flow shoot up more, which allows the rear wing to stall at a higher angle attack. Let's jump to the results to see exactly what happened with it. So in figure 12, we see the drag coefficient in the top figures, and then in the bottom figures are the lift coefficients. And the left column is for the absolute values, and the right column is for the differences. As we suspected, the lift coefficient drops a lot. It goes from like about minus 0.35 or to about minus 0.45. And that means that the booster plate is doing a lot for the downforce, but it comes at the expense of more drag, as we can see in the top figure here. And that makes a lot of sense. So in figure 13, we see the pressure distribution over the rear wing and with the booster plate on the bottom here. But it doesn't really tell us much because we can't see the suction surface of the wing. So we're not really sure what the booster plate is affecting here. I guess we can kind of conclude that maybe the booster plate is seeing higher pressure on the upstream surface, which makes sense, and that agrees with it producing more downforce and drag. But in figure 13 in the left column, figure 14 in the left column, we see the pressures cutting through the car, and then on the right column we have the velocities. And the top row is for without the booster plate, and the bottom row is for with the booster plate. So for the pressures, the booster plate is definitely increasing the pressure over the front half of the rear wing. So you can see here compared to here. But I think the rear half is a little lower with the booster plate. It's like sort of yellowy green as opposed to very green. So I think much of the downforce improvement we saw in figure 13 and figure 12 is actually coming from the booster plate, because that is seeing high pressure on the upstream face and low pressure on the downstream face that we can see here. And that produces downforce. So the reason why the back half of this rear wing suction side is higher in pressure is because the booster plate is working in that it is squeezing the flow over the suction side. But once the booster plate ends, the air is free to just escape, and we lose that low pressure now. And we see that in the velocity too. And also, given that this low pressure in this vicinity is close to the booster plate's upstream face, it is questionable how much downstream downforce will be produced anyway, because this phenomenon produces low pressure on both faces, so they sort of cancel out what would be happening on each side. So perhaps for this configuration, the only real benefit is that the booster plate for the rear wing would allow it to run at higher angles of attack without stalling, because it forces the flow to go over the wing still. It has nowhere else to go. Now in the right column, we see just how much the booster plate forces the flow up, and even really just redirecting it what is already kind of fast moving flow. So it's kind of taking advantage of that too. Now let me zoom into this bottom figure because there's something pretty cool going on here. So behind the booster plate in this lower figure, there is a huge wake, and so that's definitely a culprit of much of the drag we saw in figures 13 and 12. One thing that is a little surprising is that the low pressure behind the booster plate pulls up the rear wake, but the flow over the diffuser isn't affected too much. So let's compare these two diffusers. It's pretty much identical. It doesn't seem to shoot up any more. So the booster plate's effect on the rear wake really seems to stop at about halfway down the rear. That kind of indicates that the booster plate has just a localized effect. Let's now move on to the effect of a gurney flap on the rear wing. So in figure 15, we see this configuration with this gurney flap, and it's literally just a flat plate sticking up into the trailing edge. Gurney flaps in general, despite what they may look like, are very effective at increasing the downforce of wings. And just from the pressure plots in figure 16, so the top row, let's zoom in here. Here we go. It is clear that this is the case too. Without even looking at the forces, we can pretty much conclude that. And the reason why is because you can see over the top surface, the pressure is far higher with the gurney flap than without it. It's like close to 2000 pascals compared to 1500. And the numbers do back this up as well, because without the gurney flap, the downforce coefficient is 0.3, while with the gurney flap, it's now 0.49. So that's almost a 67% increase. So why do gurney flaps have such a large effect? Well, the pressure plots show us why, these ones here. As the flow goes over the top surface, it hits this vertical flap at the back and decelerates. That converts some of the dynamic pressure into pressure you can feel, and then that occurs directly over the top surface of this wing. So that surface now sees a higher pressure. That means that the pressure difference between the lower surface and the upper surface is higher, and that creates more downforce. And in addition to that single massive benefit, the pressure on the underside of the airfoil is also changing. As we see, it is lower. It's like bluey compared to green. So the reason for this is a little complicated, but let me see if I can simplify it. So because there is so much high pressure over the top surface, that makes it harder for the flow coming in to continue to travel there. There's this back pressure kind of forcing it out. As such, it seems that the lower pressure underneath And because that is an easier path to take, some of the air takes it. This means that more air goes underneath than you'd usually get when you don't have the gurney flap, and that means that the flow has to accelerate more. That's because viscosity limits how much air can really move around in a given amount of time. The air that goes over the airfoil now has to squish together, and that results in lower pressure underneath. Hence why we not only get so much high pressure over the top, but so much low pressure over the bottom too. So there's a two-way swing going on, and that leads to a 67% more downforce. Now, while that is great, the drag coefficient is not improved. In fact, it actually increases. It went from 0.43 to 0.512, so about a 20% increase. But when you think about it, you're getting a 67% increase in the downforce with only a 20% increase in the drag. So that is a good trade-off. So from here, the authors look at an isolated wing with like a trailing edge extension kind of thing down here. But because it is just an isolated wing, I won't go through it here because the results are different when you put it on the car. So it might get a little confusing. If you want to see the results, then you can just look at this paper. It's in the link below. But let's move on now to a really interesting idea, which is a wing that is tilted to one side. So in figure 20, we see their setup. There is literally just a wing that is higher on one side than the other. It's really novel. So let's jump first to table 3, where we see the force coefficients. So we can see pretty much everything here. Okay, so the tilted wing was pitched to two different angles of attack, 7 degrees and 14 degrees. As the angle of attack increases, the drag coefficient drops by a few percent, but I think that's within the error of the CFD, it's like 3%. Likewise, the drag coefficient drops by about 4%, but again, that's probably within the error. I mean, it makes sense that the lift coefficient will drop with the increasing angle of attack, but still, we can't tell exactly how much. On the other hand, there is quite a sizable change in the side force, so almost a 9% change. And I think that may be outside the error, and it makes sense that the side force is more at high angles of attack because the force vector from the airfoil is now pointed partially in the side force direction. So the more force the wing produces, the more side force there will be too. That helps cornering as well. Now in figure 21, we see the velocity plots over the airfoil, and these are at two different angles of attack, 7 degrees and 14 degrees. And it is clear that at 14 degrees, which is the lower one here, more of the air is stalling. So let's zoom in a bit here. Here we go. So you can see the third and fourth planes from the left. There's a huge amount of slow flow over like 2/3 of the chord of the airfoil. That is stall, and that is a huge wake. A nice coincidence is that for the second plane, because the airfoil is closer to the car, the flow underneath the airfoil gets squished and is forced to stay attached over so much of the wing. So we don't get any stall there. It's really forcing it to stay attached. However, the downside of that is because the airfoil is closer to the car, the pressure this section sees will largely be seen by the car too. So the downforce will cancel out. But the side force will still exist because the surface of the car is vertical and the surface of the wing is not vertical. So let's move to figure 20 because we see the pressure over the surface of the car with this tilted wing. Now on the underside of the wing, let's zoom in here, as you go from the left to the right, which means that the wing becomes higher off the car surface, the pressure underneath the wing reduces. That it goes from like yellowy to bluey. That makes sense because I think that as the wing gets closer to the car's boot, the effective angle of attack gets lower. And if you don't know what the effective angle of attack is, check out a video on our YouTube channel called Why the Effective Angle of Attack is So Important, Aero Fundamentals number 63. Now, when it comes to using the rear wing as an air brake, we see in the vortices in figure 22 down here. So this is pretty cool. Here we go. So the right side is producing far greater vortices. You can see massive vortices here compared to the left side. Why that is? Well, the authors don't go into it too much here, but I would suggest that it is because the wing is acting more with the car when it is lower down compared to when it is higher up. It is doing its own thing on the left side. So perhaps lower down, there is a synergistic effect with the car. Now, what we've gone through so far is all for straight line driving. What happens when you are cornering? Well, in figure 25, we see the effects of the car during a corner with a 90-meter radius of curvature. And this is with a splitter plate. So no splitter plate is blue. With a splitter plate and the booster plate not deployed is orange. Then with a splitter plate and the booster plate at 25 degrees is gray, and then with the booster plate at 50 degrees is yellow. So overall, adding the splitter plate, so the blue bit, so blue compared to orange, and not having the booster plate deployed, the drag coefficient doesn't really change very much. So this is the CX value here, but the downforce coefficient, which is the CZ value, it drops a lot, like from minus 0.04 to 0.06, so 100 count change, which I think is outside the error of this CFD simulation. Then as you deploy the booster plate to 25 degrees, which is gray, and 50 degrees, which is the yellowy one, the downforce grows more and more and reaches almost 0.25, so like a 300 count increase, and that's huge. The drag coefficient increases too, as you'd expect, but only by about 60 counts. So the downforce is definitely growing quicker than the drag coefficient, so that's a pretty good trade-off. Now in figure 28, we see the effect of having a gurney flap off compared to on during this cornering. Here's figure 28, and there isn't too much of a benefit actually. So the downforce coefficient is only improved by about 40 counts with this gurney flap, while the drag coefficient increases by about 30 counts. So this is during cornering. So I'm not sure if the gurney flap is really that beneficial. It's probably within the error of the CFD. And why is that? Well, we don't really get any flow vis here to determine that, but I would think that perhaps the angular flow might render one side of the gurney flap not effective, and that would increase the drag more too. So that's perhaps why the gurney flap doesn't work as well when you're cornering. And with that, we come to the end of this podcast. And I think this last result was a little surprising, that cornering with the gurney flap on wasn't that beneficial. Whereas with the splitter plate and the booster plate, they seem to be pretty much good no matter what, cornering, straight, whatever. So finally, much of this was done with CFD. And if you want to learn how to use CFD for your projects, and in particular OpenFOAM, which is very powerful and free but hard to learn, then take our courses in the link below. And if you're doing experiments, then did you know that you have a 2 to 4% error in your results just from changes in the atmospheric conditions every day, or even from hour to hour? In the Atmosphere Hawk link below, we go through how to fix that. So if you like this podcast, hit the like and subscribe buttons, and we'll see you on. Peace, amigos.